All right. So, hello everyone. I'm Jacopo. Joshua introduced me yesterday, and I will be teaching you for part of this week and part of next week. And we will start today with some evolutionary game theory. Okay, this thing is still not really on point, but who cares? It's likely that I will keep losing and getting it back. So if you don't hear me, just raise your hand and tell me that you didn't hear or understand what I said. So I will start this week with some game theory applications for biology and in particular eco-evolutionary game theory. And we will have some theoretical lectures today and tomorrow. And then on Thursday there will be a computational lab. I guess you've done a bunch of those already this course. So you do need to bring your computer on Thursday. Okay, so since I am starting today, I would actually like to start with asking each one of you to give me a very short presentation of themselves. I have some file where you wrote your interest and your background, but it's better to connect the names to the faces so that I have an idea of who you are. You just very briefly, you can tell me your name, what's your background, at what point of your academic career you're at, and in a couple of words your interest. So we can start here. Okay, thank you.
Hi, my name is Kelvin. I'm a biologist
Yes, thanks.
My research related to mycology and microbiome ecology, so okay. a little bit of both. I'm Rosa. I study at IMPA in the north of Brazil. My interests involve functional ecology, functional community ecology of tree species. Mm-hmm. I like to study tropical forests, so that's why I went to the Amazon.
Nice.
Hi, I'm Joaquim, and I'm an undergraduate student in biology. And my main interest is in community ecology and quantitative ecology.
Hi, I'm Pedro, and I'm a biologist. I will start my master's degree in ecology evolution, and my focus in fish movement.
Okay. Can you repeat your name? Sorry.
Pedro.
Hi, I'm Daniele. I'm also a bachelor biologist. And I intend to start my master's degree course this year, studying ecology.
Okay.
Morning, I'm Gabriel. I'm a biologist. I'm doing my master's degree in ecology in University of Brasilia. And I study the relationship between biodiversity and ecosystem services.
Hi, I am Amanda. I am a mathematician, just graduated. I'm coming here to São Paulo to start my master's degree in applied mathematics.
Hello, I'm Pedro as well. I'm a physicist, and I do a master's in astroparticle physics, so nothing related to ecology. But I'm here because I might change fields when I go to my PhD.
Welcome.
Hi, I'm Sarah, whatever. I'm a biologist. I'm doing my master's degree in plant biotechnology. I'm currently working with metagenomics, microbiome, and I'm considering going for a more ecological PhD, so yeah.
Hi, I'm Tiago. I am a physicist. I have a master's in cosmology, but my interests in biology are metapopulations and landscape ecology.
Okay.
Hello, my name is Kaluan. I am a biologist.
So can you repeat your name?
Kaluan.
Kaluan.
Yeah. And nowadays I am pursuing a master's degree in ecology, and I work with human ecology and local ecological knowledge about artisanal fisheries in Amazon.
Hi, my name is Moise. I'm a statistician. I did a master degree also in statistics, and I have worked with the use of bioacoustics and acoustic data to process to evaluate biodiversity and for the purposes of environment monitoring.
Nice.
Hi, my name is Anna. I am a biologist and I am a master's student in ecology in University of São Paulo, and my main interest is in theoretical ecology and population and community ecology.
Hi, my name is Melina. I am a biologist too, and I have a master's in ecology, working with coral reefs and species distribution. And now I am pursuing my PhD to work with connectivity, metapopulations, and evolutionary dynamics.
I am Pedro as well, and I'm an undergraduate in biomolecular physics. And my main interest in protein-protein interactions, which is not very related to the course, but I'm willing to change my mind also.
Good morning. I'm Mateus. I'm manager, and I'm pursuing a master degree in management and management control. And my work, my field of work is circular economy, water, and energy.
My name is Tiffany. I am a biology undergraduate student, and I'm currently at my very first research work in forest dynamics associated to drought events.
Hi, my name is Gabby, or Gabi, or variations, I don't care. I'm a physicist with a master's also in physics. I studied a binary model and tried to understand the transition for coexistence of both signals or just one.
Mm-hmm.
But I have many interests, and I can't decide what my main interest is.
Great.
Yeah.
Good morning. My name is Isabella. I am a biologist, and I am studying with Gabriel at University of Brasilia, doing a master's degree. And my interest is in functional ecology and biogeochemistry.
Okay.
Hi, my name is Hannah. I have a degree in natural science. I'm a master's degree in fisheries and resource management, and I work in a scientific project at the Aquatic Ecology and Fisheries Center of Amazon.
Hello, my name is Gabby. I'm a mathematician, and my interests are epidemiology and complex networks.
Hello, my name is Matheus Mariano. I'm an undergraduate student in biomolecular physics, and my main interest is in evolutionary dynamics.
Hello, my name is Paula. I am an undergraduate student in biology. I am currently aiding research in biodiversity and abundance of cyanobacteria, but one of my interests is sustainability studies, and I plan to connect that with aquatic ecology.
Hi, I'm Mikael. I'm a veterinarian and a master's degree student working on antimicrobial resistance associated with livestock production.
Can you repeat your name?
Mikael.
Mikael.
Hi, I'm Gildes. I'm environmental engineer.
I'm from Peru, but I'm studying in Brazil my master's degree, which is related to environmental biology. My research interests are in biology conservation.
Good morning, I'm Laimara. I work with human ecology. Currently, I'm pursuing my master's in development and sustainability. And yeah, I guess that's it. Oh, I'm migrating to ethnoecology.
Hi, my name is Guilherme. I am finishing my master's in applied mathematics. My research is about mathematical modeling via age-structured PDEs for, I don't know, the problem is mosquitoes' life cycles. And my interests are very broad, just like mathematical modeling and mathematical analysis for biological problems.
Hi, I'm Miguel. I'm a biologist by training. I'm part of molecular ecology lab, and for the last few years I've been studying the natural history and modeling the reproduction of carpenter ants on the Cerrado, and I'm pursuing a master's in ecology.
Can you just repeat your name, sorry?
Miguel.
Miguel.
Yes.
Okay. All right, thank you very much. This is really helpful. I may forget some names, but this is gonna be helpful to remember it a second time afterwards. So, okay, since you presented yourself, now it's fair that I present myself. So I'm Jacopo, I'm a physicist. I have been working with theory in biology for a while now. Did my PhD in Paris with Alexandra Walczak and Thierry Moray, and then now I moved on to Georgia Tech to work with Joshua Weitz, who gave you the remote lecture yesterday. And I've been working on a broad of different subjects. I worked on protein structural coevolution, I worked on viral evolution, and now I'm working on ecology and evolution of phages and bacteria with an eye to the application of phage therapy. So, yes, here I am. And so thank you for your presentation. I appreciate this is a very diverse group, which is great. There are people from different backgrounds. There's physicists, there's a lot of biologists, you have different interests. Some of you are more theorists, others seem to be more data and empirical pattern driven. I think it's a great pack of people so that everyone can learn from all the others. So yeah, very nice. So, okay, today it's gonna be on the, so I didn't load anything yet on the drive because today is purely on the board, on the blackboard. So there is really not any material, but there is stuff in Joshua's book that I will upload that talk about what I'm gonna tell you today. So don't worry if you miss something. We're gonna be talking about all right, game theory, which is a framework of mathematics that can be also used to study, among other things, problems in biology. So to get acquainted with this theme, I would actually like to start to play a couple of games with you to get some concepts down. So the first game is an auction game. And the rules are as follow. Say that I have $5 that I am gonna give you, right? And now each one of you will have to bet a number. And the person that bets the highest, so first bidder, bids X, and wins $5 minus X, okay? The second bidder will bid Y and loses Y, okay? And gives Y to me. All right, so the rules are very, these are all the rules, okay? Very simple game. So the person who bids X gains $5 minus X. This can be a negative number, in which case this person will actually have to give me money. Or the second person that bids the highest will lose everything that they bid, okay? And the minimum increment is going to be, let's say, $0.5. So, does anyone want to bet a number? You don't, you're afraid, you're shy, too early in the morning. You tell me, you go one by one. You declare your bet. It's an auction, yeah.
The minimum bet is
$0.50, yes. It's also the minimum increase. You bet $4, wow, okay. Nice. So, right now you're winning $1.
I bet $4.50.
Great, well done. So right now what's happening is that you're winning 50 cents and you're losing $4. Okay, wow, okay, this is a wild one. Okay, so right now you're losing $15. And and you're losing $4.50. Okay, this is an interesting outcome. Does anyone want to raise?
Raise from 50? No.
I don't know. I mean, I'm just asking. I'm a greedy bank. I want to win as much money as possible.
I bet 20, 50.
No! 21.
All right, you bet 21. The problem though is that you're now losing $16. Okay. What?
50. What happens now?
If you bid 50, okay. When you pass this threshold, the more you bid, the more you're going to lose. Okay. So now, if you can bid 50. Now, if you bid 50, you lose 21 instead of 16, which in a way it's an improvement, and you lose 45. So, okay, this went wild really quickly. That's nice. I don't know if anyone wants to lose more money.
Okay, 55.
Okay, great. Amazing. So, yeah, right now you're losing 50 and you're both losing 50 actually right now. Yes. The minimum increase is 50 cents. And 50 cents. Okay.
One thing I didn't understand, but I guess I was not paying full attention, is why if I lose more, then he loses more than he was losing before. Like he was losing 16, but
Yeah.
then I bet 50, I was losing 45 and he was losing.
Yes, because before he was losing, in fact he was winning 5 minus 21, which is minus 15, so he was losing, 16. And then since he was the second bidder, he was losing Y, which is 21. So he was basically losing the other 5 on top of that.
Also, every time someone else bids, then the person starts losing also the 5, because I'm winning the 5 now.
Yes, exactly. Yes. The problem though is that when you pass the threshold of like 5, any higher bid you put, it's actually it's worse for you, unless you were not in the game before. Okay, this is great. I mean, this is really nice. Usually what ends up happening is that in the beginning when people are betting below $5, maybe I should have started with 20, but when people bid below 5, many people are bidding because they think they could win something out of it. But then at some point, all of a sudden, you approach this threshold and you pass it, at which point typically you have only 2 players playing, and because they want to be the one that loses less. And so you engage something which is called an arm race dynamics. So it's not exactly what happened today, but a little bit like that, because you kept, even though you were losing money, you still kept bidding, which it's something that happens. Usually it happens only with 2 people though, that are the ones that are basically fighting themselves. In a way, you were some of you were very generous to bid so that the other person would lose less money. That's also a possible strategy to this game. It's not like there isn't a written rule of how this should end. It's just, I mean, it's an emergent social dynamic, so it's always interesting to see how different groups of people behave given this problem. Okay, so maybe it wasn't a great example of an arms race dynamics, but I think it was a good example of the fact that sometimes when you're trying to fight for some resources, in this case the bids, there are situations where you find yourself at a point where the cost for competition becomes bigger than the gain. Okay, like in the case now where you were bidding to compete in the game, but at the same time you were actually losing money by doing so. Yeah.
I think it's a silly one, but it's just.
It's a silly question, but is game theory that game is game like something that I hunt, or it's game like it's a game that's happening?
The game theory is a broad mathematical framework that is thought to study, the theory behind games in a broad sense. And this is a game, okay? And there is no theory behind it. I mean, I'm just giving an example here of some dynamics that can emerge when groups of people or individuals compete. You have a competition for resources. You have some sorts of competition. Now the resources is money, if you want, or losing less money. That's also a resource in a way. And competing itself brings a cost, and sometimes this cost exceeds the gain. Now, if you were to have a situation where you only had 2 people racing on one another in order to be the first bidder and get those $5 and raising by 50 cents at a time, then you would engage in arm race dynamics. This time it was, if you want, it was still a source of arm race, but with more players than 2, if you wish. You had a comment? Someone there, I think? No? Okay. All right. So this was the first game I wanted to play. I don't know if there are doubts, like either on the game or on the dynamics that emerged, or comments. Yes.
So here it becomes clear that the first and the second player are going infinite, right? If they want to lose the least amount of money.
Yeah.
But in a biological setting, maybe fighting for resources, even though you're losing, can be advantageous if you exclude the other competitor, right?
So, and how you would exclude it here by bidding essentially more than $5 more than what they bid before? You mean you would exclude it by making your bid so inconvenient to go above that they would not continue the race? Is that right?
Yeah. So in a biological setting, maybe you would spend more energy searching for food, just so there is not for the competitor. I mean, it's not rational, but.
All right. Yeah, I see what you're saying. Yeah, I mean, if you want, it's a little bit of what happens here as well. Like, okay, of course, in practical terms, it cannot go to infinity, but you do have these psychological, instinctual, whatever that is, push for competition when you want to win some or lose less resources than the other. Yes. Yeah.
I guess I am having a hard time thinking of an example of a case where the cost is actually higher than the gain, and I was imagining some stuff like humans, we lost a lot of our defense systems, I don't know, because we put our energy in getting our brain bigger,
yeah, you could say.
But that still was a gain, and if you could give some examples.
Yes, so I can. We'll go into a little bit more theory later, and I hope that the conceptual framework will become clearer. But to your point, one possible example is microbial coevolution. So you can take some microbes. Let's take the example, like the most, one of the most studied examples is the coevolution between bacteria and phages, simply because it's one of the first instances in which evolution was observed by Lurie and Delbruck at the beginning of the 20th century. So you have some bacteria with their nasty stuff, and some phages that are viruses that infect bacteria, and these two can engage in coevolutionary dynamics. I mean, there are many experiments of that, and since most mutations are deleterious, in some instances, actually by trying to become resistant to the virus, some of the bacteria will actually die, just because they are. And this is a clear example of one of the situations where the gain is lower than the cost, because actually by trying to become resistant to something that might or might not kill you, you almost doom yourself to extinction. Now, it doesn't happen always, right? Otherwise, evolution would never work. But there are instances in which you accept very bad trade-offs, like you can mutate and develop resistance, but you don't grow anymore, for instance, or these kind of things.
I was just curious about what Thiago said, and did you mean like an inconvenient bid before this threshold, like before the $5? But then it feels like once you go beyond the $5, the bidder that increases the least gets the advantage, you know, like a relative advantage. Because, for example, if the bid is at $5, then the person is winning nothing. Sorry, I'm trying to. But when I bid with Gabi, she was betting 20.50, and then I bet 21.
Mhm.
Then I started losing 16, and she lost 20.50. You know,
Right.
so like I had a relative, even though we were both losing, I had a relative advantage beyond.
Right. Yeah. So when it comes to yes, that is something that sometimes happens. But then when someone raises 25 more than you, like and then like raises to 50 compared to your 21, maybe at that point you don't want to raise anymore. So that there it's a little less clear whether you still want to compete or you're fine with just losing whatever you had put. But yeah, if people raise by little amounts, that's exactly what usually happens with this game. Like the two people start raising by 50 cents, and it's only those two people that play. So the other implicit concept here, implicit in the fact that there is competition for resources, is the concept of relative fitness, right? It doesn't matter that much that you're losing something as long as you are not the person that is losing the most. Something like that. Okay, great. So now we are going to play another game. I hope it's gonna go as well as the first one. This was really cool. And so we are gonna divide, well, you are gonna divide yourselves in pair. So you choose like someone to play with, like by proximity or, well, you should be close to one another. In the meantime, I write down the rules. So are you divided? Great. So the game goes as follows. There's going to be in each pair. There's going to be a player A and a player B, and imagine that I'm giving $2 to player A, but then player A needs to propose a sum less than $2 to player B, and if player B accepts this gift, then B gets X, whatever he gets offered, and A gets $2 minus X. So essentially, A needs to take some part of these $2 and offer it to the other person, to B. And, but if B refuses the offers, neither A nor B get anything. Okay? So let's say that I offer something and you say no. None of us gets anything. Yes?
How many times do we play?
Just once. Excellent question. All right. All right. I'm gonna start. Sampling the results. So what happened here?
$1 for each one.
And you accepted. Okay. Great.
Use the mic because Ruth is watching from home and he can hear us if you don't use the mic. There's a person sitting at home.
Okay. So the first pair, I can actually summarize. The first pair, they offered $1, so half of what they were given by me, and they accepted. How about you?
$1 also.
Okay.
So I offered him 1 cent and he accepted.
Okay. Very good, very good.
He offered me $1 and I accepted.
Okay.
I offered 55 cents. No, I'm sorry, 56. He didn't accept it.
He didn't accept. Okay, wow. That's fair.
I also offered 50 cents and he didn't accept it.
Okay. Please.
We propose 50 cents and I accept.
I offered her $1 and she accepted.
How much, sorry?
$1.
$1. Yes.
He offered $1.10 and I accepted.
Okay. Wow.
I offered her 10 cents. She said no.
Oh, okay.
I offered $1 and he accepted.
I offered $1 as well and she accepted.
Okay.
$1 accepted.
Okay.
I made 3 offers because I guess I didn't get the game right. And they were 10 cents, 50 cents, and $1, and he refused them all.
Okay, wow.
Yeah.
So tell me again, 10 cents?
10 cents, and then 50 cents, and then $1. Yep.
Okay, interesting, great. We even have an instance of repeated games. All right, great. So this is very interesting. Okay, this is a standard game that is played in classes of people studying business and finance. And what usually happens in those cohorts is that everyone offers on the order of 1 or 10 cents, and everyone accepts. Okay, so this is the standard outcome if you play this game in a class that studies business. And the reasoning for them goes, it doesn't matter that you're getting much more than me, I'm still getting something, and therefore I'm going to accept your very unfair bet. But statistically, when I play this game in cohort that study biology, ecology, you folks have already in your mind the concept of relative fitness somehow and resource limitation in your hardwired in your way of thinking. And therefore, outcomes like this are much more prevalent, where you tend to offer close to the half, and most of the people actually accepts. We have some exceptions, so like the third pair who offered the 1 cent, like in those standard game theory classes for finance, and I guess the reasoning was the one that I just, it was the 2 of you, right? Yeah. So I think the reasoning was the one I just said. It probably should have been something similar. But I think all the rest of the people that offer close to 1 discussed a little bit, and they were like, okay, but I don't see why I should accept something less than you. And therefore, they all offered something close to half. Now, and people that were offered less, like 50 cents, 56 cents, is also interesting, and they denied. I mean, it also goes to reinforce, I think, this way of thinking. Then we have someone here that was really afraid to lose any money, so they went even above, but it's still within 10% of half. So I mean, it's not an outlier, but that's still interesting. And this is very interesting. Like I don't know what you wanted to get from this from this game, but it's a very interesting outcome. You wanted to get as much money as possible. Maybe if this continued more than 3 times, you would have gotten $1.50.
No, he only wanted that I gave him everything.
Ah.
He only wanted $2.
Okay. Well, then I guess you were doomed to both not getting anything. Yes. Someone, the mic.
Does the statistics change a lot when like the player B doesn't know the amount of money that player A has?
So,
like
okay, that's interesting. I've never thought of that. That's an interesting variation. I'll think about that. I don't know. Okay. Yeah, that's an interesting one. It requires much more interaction. I mean, it's a longer game because then you need to lie and like it's a little bit more complex. But okay.
Okay,
cool.
Thank you.
Maybe another day we'll play that game, but I need to I need to go on with the class now. But okay, this was very instructive. So once again, here in the statistics of these bets and answers, I think I can say that you're already thinking in terms of like relative fitness and resource limitation. So why resource limitation? Well, the point is, if resources were infinite, you wouldn't care that someone else has more than you, right? As long as you have something. Whereas if resources are limited, then this other player that has even just a little bit more than you could capitalize on that, and you will be forever worse off, essentially. So this is a little bit why these two concepts are related. And you will notice that I'm already using terms from the vocabulary of evolution, such as fitness. I will clarify this between today and tomorrow. And hopefully it will become clear why this game theory applied to biology goes by the name of evolutionary game theory. Okay. Are there questions at this point? No, good. Yes, please go ahead.
I'm having a hard time again, I guess, with the conceptual frame, maybe, because you talked about a cost being higher than gain, and the bacteria like trying to survive the virus or something like that. And okay, I guess I'll be more specific. The bacteria has to survive the virus or go extinct, right?
Yes.
And then,
well, you can have coexistence, but
what is the situation where she dies? Because like mutations are going to happen, and some will be good, some will be bad.
Right.
A lot of them will end up being bad.
Yes.
But if the species survives...
Also, good and bad depends on the context, right? So, I mean, if you like, you can have bacteria and viruses infecting them. This doesn't necessarily mean that the bacteria go extinct, though. I mean, some of them will die, but the population of bacteria won't necessarily go extinct. It will in certain cases, it won't in others. But the process of evolution, I mean, mutations happen randomly, and then it depends what gets selected, right? And some of these mutations, again, are good to survive the viruses, but are bad for other things, right? So, for instance, you stop growing, you don't grow anymore. And like some part of your metabolism gets, broken, and you grow very slowly, or some bacteria have pili to move, and some resistance mechanisms involve losing the pilum, so you cannot move anymore, essentially. And when you find yourself in another environment where moving is important to get food, then you're like this mutation you had that seemed to be good to survive the virus will basically condemn you, right? So I mean, it depends a bit on the context, but I mean, sometimes you have these situations in which in a one-to-one match you accept something that then turns out to be not good for you. So I will continue, and we will see this again. So maybe this will become a little bit more clear, but please go ahead.
Yeah, I'm just wondering, like, I guess it's a little bit like her. I'm thinking about these processes in nature. So I'm thinking, like, how exactly does this happen? Does this has to be... I'm sorry.
Are you talking about the bacteria and fishes, or are you talking in general?
Yeah, I'm talking about like this example really, like where it's like a trade-off between A and B. And does this need to happen in some specific ways? Like, I don't know, maybe these two species clashing together, like in a fight, actually like going aggressive against each other, or can it just happen like in a more passive way in which Like they don't directly interact with each other,
okay.
but they're
This is a matter of, okay, this is a little bit of a more philosophical question, in the sense that it becomes a question of how you decide to model a certain system. It can be both, okay? I mean, you do have direct interaction that lead to some of these things. For instance, I don't know, imagine lions that hunt together, and you have a dominant lion and a less dominant lion, and then the dominant lion eats most of the food, right? I mean, these are actually things that do happen in nature, right? I mean, with direct interaction, or the species that co-evolve with one another. Then you have more subtle situation in which maybe there is an implicit like competition for resources, but there becomes a little more tricky. For instance, you have, but that's still a direct interaction. You have microbes. Okay, let me give you some examples of like behaviors of what happen that actually happen in nature. So, and then what you call direct and indirect. I mean, you tell me, because it's a little bit of a classification. So I'm not sure precisely what you mean there. Okay, so we saw a bunch of concepts, and again, we have some games that are critical in nature. For instance, again, you have some alternative actions or behaviors which in the game theory vocabulary are called strategies. And that have an effect on the survival either or the reproduction either of a individual or a species altogether, which in game theory is called a payoff. Okay. All right. So, for instance, these actions could be, for instance, to defend or retreat. For territorial animals, okay, that are defending their territory, and they need to decide to what extent are they going to engage in fights where they can get hurt, or they will let some other individual get into their territory. Or in predator-prey dynamics, this could be for the predator. Whether you will attack or whether you will wait. Because if you attack and you're not ready to get the prey might escape, and then you're not going to get it afterwards, right? And if you're the prey, you may want to decide whether you want to forage, so go out and eat, essentially, or you want to hide. Clearly you cannot eat while hiding, right? Think about the lions and the gazelles in the savannah. I mean, sometimes you can hide in some places, but you cannot really eat there, and sometimes you need to go out in the open, and then the lions can hunt you. So, I mean, these are actual, like, actions and decisions that animals and organisms need to do on a daily basis, and they have an effect on whether these animals will manage to eat and therefore manage to reproduce, or they will get eaten and therefore die. So this is a little bit of the concept behind this game theory framework. Also, there is another example from microbes, another one I didn't give you yet, which is the fact that you have some microbes, some bacteria that have some enzymes that produce common goods. That they need for their metabolism. And of course, producing these common goods has a cost, because it comes at the expenses of whatever energy they need to give to the enzyme to make this process. And you have, and they produce it, and then they reuse it. And you have some other microbes that only use it without ever producing it, which are called these are called cheaters, defectors, and these are called cooperators. And we will see cooperators, defector games tomorrow, actually, a bit more in detail. But so these are some sets of rules and actions that it's a way that we use to think about these biological situations. Of course, it's not like the animals think about it in this way. They just, they just go and hunt. But we, as modelers, try to conceptualize the dynamics that happen in nature with this framework. And the reason, which you will hopefully see in a moment, is that thinking about this in this framework allow you to use a set of analytical tools to produce predictions in this system that otherwise you would not be able to make. Essentially, this allows you to do some math on the system and get a set of predictions, or understand certain behaviors. Okay? So let me give you yet another example. And in fact, this is where I'll try to introduce a little bit more theory also on this subject. And hold your questions for a little while, because maybe they will become clearer in a moment. If they don't, I'm happy to take them afterwards. So one of the most presented examples, paradigms for game theory in biology is the hawk and dove game, where it's a two-player game. And where hawk and dove are the strategies, where you have a strategy which is an aggressive strategy, and another strategy which is more cooperative. Hawks, everyone knows what a hawk and a dove is, right? I mean, it's like the hawk is that bird that kill the mice and other things, and the dove is a symbol of peace, so it's this small white bird which is really cute, right? Okay. So imagine a situation where these hawks and doves are competing for nesting sites. And if you can either have one dove that competes with another dove, or you can have a dove that competes with an hawk, or you can have two hawks, okay? These are the three possible combination of antagonist pairs that you can have in this two-player game. And the idea is, if one player gets a nesting site, it's good because they will be able to spend more time reproducing. So I mean, in general, for their population, it's going to be a good thing. Now, what happens if you have two doves If you have two doves competing for the same site, we say that the dove, since they're both doves, gets a payoff. This is called payoff of G half, meaning this is a gain. This is the gain you get for getting the nesting site. And it's divided by 2 because they are the identical particles, therefore half of the time is going to be one of them that wins and the other half of the time is going to be the other. So you have like half of the time you will be spending G time in the nesting site and will be able to reproduce, okay? Whereas if you have a dove that competes with a hawk, that's not very good for the dove because they're smaller and not as aggressive. So the payoff for the dove is going to be 0. The dove will never hunt the hawk away from the nesting site. And the payoff of the hawk is going to be G, okay? The hawk always wins and gets the site. Now, what happens when you have two hawks? When you have two hawks fighting for the site, they are very aggressive, so they will actually fight for the nesting site. Therefore, there will be a cost associated with the competition. Just in a similar way as you had when you were doing the auction game and you were trying to race over the other players. So there is a cost associated with competition, and the overall payoff is going to be a trade-off between the gain of winning the nesting site and the cost of the competition. You could think of it as one of the two hawks wins essentially effortlessly, and the other hawk loses very bad, paying a cost C and doesn't get anything. And again, since these two are identical, this happens half of the time. There are several parameterizations, but this is one possible way to think about this. Okay. The important thing is that you have a trade-off between the cost of fighting and the gain of winning the nesting site. So this is the essential ingredient of this simple model. Now that I told you the payoffs in the case of the different pairings, we can build something that is the basis for our theoretical analysis, which is the payoff matrix. Meaning you have a player 1, which is the focal player, which can be either a hawk or a dove. Again, these are what is called strategy. So again, when a hawk plays against another hawk, you get G minus C over 2. When a hawk plays against a dove, you get G. When a dove plays against a hawk, you get 0. And when a dove plays against another dove, you get G over 2. Okay? So I'm basically rewriting these in a more compact form. And this is a matrix where each entry tells you the payoff in the case of each pairing. All right? Now that we wrote this matrix and we gave quantitative numbers to the payoffs, what can we say about this system? So the best strategy, of course, will depend on the parameters of this model, which are the gain and the cost. Okay? For instance, if the cost goes to 0, there is no cost in fighting for the hawks. I think you can intuitively imagine what's going to happen. The payoff matrix is going to look like something like G over 2, 0, G over 2, okay? Therefore, playing the hawk, if I'm a hawk, I play against a hawk, I get G over 2. If I'm a dove and I play against a hawk, I get 0. And so being a hawk is better if you play against a hawk. In the same way, if you're a hawk and play against a dove, you get G, and if you're a dove and you play against a dove, you play G over 2. Therefore, it's better to be a hawk also if you play against a dove. So it's always better to be a hawk. All right, so I mean, this is intuitive, right? If you don't pay any cost and you're stronger, why would you play the weaker player? Now, if C is bigger than G, now things get tricky. It means you will always win against the doves, but when you play against your own kind, so a hawks, actually you're paying a bigger cost than what you're gaining on average, okay? So the matrix is gonna look something like a negative number, G over 2, 0, okay? So now this is bigger than, this entry is bigger than this entry. Therefore, against a dove, it's still better to play a hawk. But against a hawk, it's actually better to play a dove now. You see? So now the thing got complicated, and what the best strategy to play depends on the context. Okay. Are there questions on this, on what I told you so far about the hawk and dove game? Good. So yeah, please.
But in this case is that we're not analyzing, we're only considering two individuals fighting with each other, right? We're not considering like large numbers of one individual and then a small number of the other individual.
So we are considering a situation where you have two individuals fighting against one another, but these two individuals are going to be drawn from a population. And now we'll tell you, so now we'll tell you what I mean by context. But yes, it's always one against one. It's a two players game. Yes.
In that case, the best strategy depends on the density of...
Yes,
yeah,
exactly,
okay, that's,
yes.
Okay, thank you.
Yes, please. Yeah.
So I understood your explanation, but now when I read what you wrote, it seems odd to me. It says, against the dove, it's better to play the hawk. But against the hawk, it's better to play the dove?
Only in this case, if the cost is bigger than the gain. So if the cost is bigger than the gain, it means that on average, when a hawk plays another hawk, you get a negative number. Because it's true that at some point, sometimes you're going to get the the nesting site, but the fights are going to be very costly. I mean, you can, I don't know, lose a wing or whatever. I don't know what they do to each other, but they're not very nice. So, of course, that's not true if the gain is bigger than the cost. If the gain is bigger than the cost, it's always better to play a hook. Other questions? Yes.
I'm interested in applications of this theory. For instance, I don't know if I'm like thinking too much about it. Could we apply this, for instance, the discussion of mutualism relationships? Because I remember there have been a lot of discussion about previous considered mutualism relationships not being very mutualistic, because mutualism is predicted as being as 50-50, both individuals win, but there are a few typical mutualistic relationships such as lichens that the one people thought it was a 50-50 maybe wasn't 50-50 anymore. So could this be applied to this discussion?
Yes, definitely. Like not exactly this model, but framework like game theory, which is also why it was called at some point evolutionary game theory, can definitely be applied to think about mutualism and competition in ecological situations. Yes, there are many works that try to even motivate from an evolutionary standpoint the evolution of mutualism using game theory concepts, saying that mutualism makes a community more stable or whatnot. There's many work by Novak. I think he was one of the main, one of the people that pushed this idea the furthest. But yes, it's definitely possible to use this framework.
Was it maybe the basis for this discussion, or it's not necessarily?
Well, I admit that I'm not familiar with the exact discussion you're saying, so I cannot tell you whether it was the basis or not. But I do know that game theory can be used to address mutualism in ecological communities. Yeah. All right. So. Okay, so as we pointed out, now for certain parameter values, what's the best strategy depends on context. Therefore, I need to tell you, since it's only two players game playing against one another, what do I mean? What I mean is that there is a population of players parameterized by a fraction x, which is the fraction or density, if you wish, of hawks, okay? So when x is 0, all of your populations are gonna be doves. When x is 1, all of the populations are gonna be hawks. Whereas, this is x, whereas in the middle you have a mixed population of like some hawks and some doves, okay? Then what you do is that you draw at random two players from this population, and you ask, on average, after this sampling, what is the payoff to either one of the two players? So, in math terms, this means that the P of a hawk is going to be x, which is going to be the fraction of time on average that you draw a hawk. Who here has never seen random variables and sampling problems? Okay, great. So on average, you draw a hawk x fraction of times, okay? Therefore, you have x times g minus c over 2 because this is the payoff of a hawk against a hawk, okay? P, H, H, so it's this entry of the matrix. Plus 1 minus x, which is the fraction of time you draw a dove, times g, okay? Which is equal to g minus x, g plus c over 2, okay? Yes, please.
Just a quick question. When you say draw a hawk and draw a dove, you mean draw them as opponents in this game?
Yes.
Okay.
Exactly. And then if you have a dove, the payoff of a dove is going to be 0 times x, because when you draw a hawk, you don't gain anything, plus 1 minus x times g over 2, okay? Same idea. I just took the average over the sampling process of these matrix entries, okay? So if we actually draw the payoff as a function of the population this is the payoff of a hawk that goes from G to G minus C over 2. And this is the payoff of a dove. And so you see that if G is bigger than C, which is bigger than 0, what happens is that the payoff of a hawk is always bigger than the payoff of a dove, which is what we said before. I mean, it's always better to play the hawk, okay? At the same time, you also see that if all of the population is a hawk, the overall payoff is actually lower than the payoff if all of the population was a dove, which is something we're going to see more in depth tomorrow with another example. But I mean, the important point is that you see that the payoff of a hawk is always bigger than the payoff of a dove, okay? Whereas if C is bigger than G, you see that after X star, a critical composition threshold, sorry, the X star is actually this one. It's actually better to be a dove than it is to be a hawk. So indeed, what's best to do depends on the composition of the population. Yes?
Sorry, what's that last line you added?
What's that?
The last line you put on the graph.
X star. I call this X star. It's a critical value of X for which these two payoffs become the same. So in other words, yes, this is when the cost is bigger than the gain. So this value G minus C over 2 is below 0. This is 0.
Okay. And the others was when the cost was lower than the gain?
Yes, the other one is when the cost, when the cost is lower than the gain. Yeah, my handwriting is not great. Sorry about that. All right, yes.
Just a few questions from before because I thought I had understood, but I think I didn't.
Okay.
First question, when a Hulk plays against a Hulk, why is it G minus C divided by 2? This divided by 2 is confusing me. Why is it divided by 2?
It's just a parameterization of the model. So you could, you could choose whatever, but in this case, you can. I think of it as when I win, I get G, and when I lose C. Okay, but then that's going to happen half of the time because a Hawk is identical to another Hawk. So you divide by 2. You can choose whatever parameterization you feel like, but this is the one which is more intuitive to me. Maybe it's not. It's a subjective thing.
I'm not sure. It's hard to put my question into words because I understood the Dove case because gain under 2 because they are cooperating. But in the case of the Hulk, I would only imagine G minus C. I wouldn't see the need to divide it by 2.
Well, there is no need, but I chose to divide by 2 because to me, since they are identical, something is going to happen to either one of the two half of the time.
Okay.
Again, it's a parameterization of the model. You can choose whichever you like. It's not. It's not like anything that I'm telling you changes if we remove that over 2.
Sorry, I just wanted to say that I think the idea is that here we're talking about gains in average. So if the Hawk wins half of the time and loses half of the time, then we have G plus 0 divided by 2 because we're basically making the average of a random variable maybe. So I think that's the idea.
That's one way to think about it, yes. But again, you can parameterize this problem in other ways, and it doesn't. The results don't change. You're still going to have this transition from a case where the Hawk always wins to a case where you actually have composition threshold where the Hawks don't win.
Okay.
But it makes sense when they both cooperate, both win. When they both compete, both lose. So it makes sense to be that mutualism is positive for both players, and competition is negative for both players. So in ecological way of viewing this, it makes sense to divide by 2 as well.
That's because I'm thinking G minus C for one and the other. That's what I'm That's the other mic. Yeah, the other mic. The other mic.
Well, it makes sense in a mathematical point of view, dividing by 2 because it's a sample, an average, but it makes sense in an ecological point of view because when you compete, both lose. When you cooperate, both win. So you divide the gain by 2 and you divide the cost or the gain minus cost by 2 as well.
All right, so it's very good to think about ways to think about a model, but at the same time, I don't think we should focus too much on that right now. I'm happy to discuss a little bit later about this, because again, none of the results I'm telling you depend on this specific choice of the parameterization, but it's a fair question.
Oh, okay. Just to the second question, what is X exactly?
What is?
X.
Right, that's important. X is the fraction of hoax. Okay? If you have a population, it's what fraction of this population is composed by hoax. If it's 1, they are all hoax. If it's 0, they are all doves. And if it's something in the mean, you have like some mixed situation with some hoax and some doves. Yes. And this is actually very important because of, I mean, then once you realize this, you know how to write these payoffs. Otherwise, you don't know how to write this, okay? And in the last 5 minutes, and then we'll redo a little bit tomorrow, but I just would like to close the lecture by giving you a pitch of what we will do tomorrow. So, of course, one can solve for this X star, okay? You just need to solve for PD equal to PH. And, okay, I don't have time to do the math, but you can convince yourselves that X star is equal to G over C, which makes a lot of sense in the sense that this is below 1, and therefore this is actually a frequency only if C is bigger than G. But, okay, why did I tell you this? What's the point of like thinking of a population that is mixed of hoax and doves? I mean, the population is not going to stay at the same X for all times, right? I mean, the whole point of this is that these payoffs will translate in some gain for type H or type D, and therefore they will determine how the population will evolve in time. Therefore, they will tell you the time evolution for X. So this is why this is actually very useful. So, and again, we'll redo it tomorrow, but so if you have X, which is the fraction of hoax, then X dot, the time evolution of the fraction of hoax, is going to be given by RH minus the average R, where R is fitness, times X, okay? And then, okay, X doves is only equal to 1 minus X hoax, so you don't actually need to write an equation for it because it's constrained. So the average fitness it's X times RH plus 1 minus X times RD, okay? Now, if you use this, you see that X dot is equal to RH times X times 1 minus X minus RD times X times 1 minus X. Therefore, X dot is equal to X times 1 minus X times RH minus RD. So this is a time evolution. This is called replicator dynamics. Which tells us, given the fitness of a type H and a type D, how the population will the relative fraction will evolve, okay? Now, why did I tell you this? The point is that in our framework, we say that RH is equal to PH, and RD is equal to PD. Therefore, knowing the payoff and the payoff matrix for this system allows you to write down an equation for the fraction of the number of Hawks. Yes?
Just a comment.
Yeah,
I don't
please.
know if everybody is aware that this symbol means average. It's a
Okay.
notation that maybe not everyone saw here.
Thank you for the comment. Yes,
Don't
that's,
worry, yeah.
yeah. So this is the that's an average fitness. Which is it's this one, okay? The average fitness is the fitness of H times X plus the fitness of D times 1 minus X, okay? This is just the sample average of this fitness R. Therefore, this, in the parentheses, it's a relative fitness, okay? And just as a last note, I will not do it neither today nor tomorrow because there's not going to be time, but you can actually derive this equation, okay? If you start from, this equation is not given by some god of math. I mean, you can, by first principle, you can derive it. So if you have a population of a player 1 that grows with a Malthusian fitness R1, then you have a player 2 that grows with R2. If you say that NT is equal to N1 plus N2 and that X is equal to N1 over NT, and you apply the chain rule, you get exactly that equation, okay? So this is actually the underlying exponential growth. These correlations that you get here come from the fact that you're looking at frequencies, and frequencies are constrained, okay? You can, I mean, if you want, you can do it as a homework. But the only ingredients you need to prove this are those. Yes?
But is this association of fitness and payoff always valid in the models we're going to deal with, or you depend on the context of fitness?
Let's say that in this case, we draw the analogy between payoff and fitness in the sense that, if you remember, I told you that those were competing for nesting sites. Therefore, in a unit time, they will spend G time. You can think of it as a rate, okay? So for per unit time, they will spend G time on a nesting site if they win. Therefore, these entries are reproduction rates, which is Malthusian fitness. So this is, but you always need to be a bit careful when you think about modeling of these systems that the units are actually consistent, yes.
Thank you.
Sure. I will, I know I went a bit fast on this last part. I will redo a little bit of this tomorrow, but I wanted to finish today with knowing this is not just some static thing. I mean, writing down this matrix actually allows you to study the time evolution of the system. All right. So I will load some material covering part of today's class and tomorrow's class on the Google Drive. It should be in the folder that has the same name as the title of this course. And there's going to be a subfolder called Game Theory, and the material is going to be in that folder. You don't need to do anything for tomorrow. If you want, you can try to derive the replicator equation from that, but you don't have to do it. Right? All right. Thank you.